previously we outlined the different types of activities that we encounter in our domain. Now, with event-first domain-driven design, when we are defining what those activities are, the reason that we're doing it is in part to help us drive out what our bounded contexts are, but also to help us define what the objects are that we're going to encounter within those bounded contexts. So let's have a look now at what types of objects we are going to see when we start diving in more deeply into a bounded context. So one of the objects that we're going to encounter is what we call a value object. Now, a value object is defined by its attributes. So we see the example here of an address. In the first two boxes, we have an address which is 1234 Play Street in the city of Loganville, the state of Arkansas, that's not a typo, and the country of Lightbendia. Now, if you look at the second box, you'll see that it's identical. It has the same number, street, city, state, country. Because they are identical, we can say that they are the same address. We know that if we go to either one of those addresses, we will end up at the same building. That's the nature of an address. So that represents a good example of a value object. Because of the nature of a value object, it has to be immutable. The reason it has to be immutable is because if we change any one of those fields, it becomes a different address. So in the last example, we see that we've changed the street from Play Street to Reactive Lane. And when we do that, it's no longer the same building. It's no longer the same address. We're now going to a different location. Therefore, we can say that the value object has to be immutable because any change to it causes it to become a different object. Now, these are typically state containers. They contain data that is often passed between different components in a reactive system, but they can contain business logic as well. So if you want to have some logic that extracts some information out of the address, that logic can exist inside of the address object. In a reactive system, messages are implemented as value objects. So we talked about the message-driven architecture of a reactive system. These are the messages. They are implemented as value objects, and then they are passed between different components in your reactive system. Now, to contrast that, we also have something called entities. Now, an entity is defined by a unique identity, like an ID or a key. So if we look at our example here, we have our person, John Smith, in the first box there. Now, John Smith is going to be defined by a single identity, which in this case we've chosen to be name. Now, I realize that name in a real use case is actually a terrible unique identifier, but we're going to use it in this case just so I don't have to try to recite a UUID or something like that. So we're going to say that for our domain, for whatever reason, John Smith or his name is an appropriate unique identifier. Now, if that's the case, then we can look at John Smith's attributes. We can see that he's 5'11", 185 pounds with brown hair and blue eyes. But if we compare that to the second instance of John Smith, we see that the name is the same, but some of the attributes have changed. So his weight is now 175 pounds, so he's lost some weight. That's good for him. And it looks like his hair color is now red instead of brown, so he bought some hair dye. Okay, no problem. It's still John Smith. The person hasn't changed because, again, he is defined by his unique identifier, which is his name. The attributes have changed, but that's okay. Now, on the flip side, if you compare that to the last box, we see Jane Smith. Now, in this case, our unique identity has changed. We don't have the name John Smith anymore. We now have the name Jane Smith. If you look at the attributes, you see that the height, weight, hair color, and eye color are all the same as our last version of John Smith. But we can say that this is not John Smith. This is Jane Smith. This is a different person. So what we're saying here is with an entity, first off, entities, unlike value objects, can change. They are mutable. So the attributes can change and it can still maintain its identity. Entities are the single source of truth for a particular ID. So if you want to know anything about John Smith, you can go to the John Smith entity and he can give you those answers. He can tell you his height, his weight, his hair color, his eye color. So it is the single source of truth. Entities are often workhorses for mutable state, but also for business logic. They often contain a lot of business logic that says things like, when I want to change a particular attribute, this is how I do it, and these are the rules associated with that change. In reactive systems, if we're building using akka, actors are an excellent model for entities. They have a unique identity in the form of an address. They are mutable. You can change their state in a safe way. So they make excellent representations of entities. Logam is built on top of akka actors and actually rename or takes that concept and gives it the exact name out of domain-driven design. It calls them entities. So we talked earlier about how in reactive systems you'll often see a lot of the domain-driven design terminology in those systems. This is an example of that. There's also a specific type of aggregate which we call, a specific type of entity which we call an aggregate. Now, an aggregate is a collection of domain objects bound to a root entity. So here we see a person that consists of a name, an address, and a phone number. That name, address, phone number, and person make up an aggregate. Now, the root entity here, and it is always an entity, is called the aggregate root. So the aggregate root in this case is the person. Objects in an aggregate can be treated as a single unit. So you can say that a person consists of a name, an address, and a phone number, and those are all part of a single larger whole. Access to objects in the aggregate have to go through the aggregate root. Remember, an entity is the single source of truth for any particular piece of data. Same thing with same thing with an aggregate. It is the single source of truth. So if you want to know the truth about that person, you have to go to that aggregate root of person. You can't, go directly to the database because the database is not the source of truth. The aggregate is the source of truth. And we'll get into this in more detail later in the course. Transactions should not span multiple aggregate roots. So if you find yourself in a situation where you need to do a transaction that actually crosses aggregate roots, then you've either defined your aggregate roots incorrectly or there's a problem with your transaction and you might have to rethink it a little bit. Aggregates actually make really good candidates for distribution in reactive system. So when we start looking at other things later on, such as cluster sharding in akka, for example, that is something, a good place to start looking to distribute with cluster sharding is your aggregates. Logam uses the concept of a persistent entity, which is backed by cluster sharding, and it distributes those entities or those aggregates across a cluster. So that's a good starting place to start distributing. But how do we determine aggregate roots? Aggregate roots are very important in a domain-driven design system, but figuring out what they are is not always straightforward. There's a few problems. One is the aggregate root can be different from one context to the next. So in reservations, we've decided that the aggregate root is going to be reservation, but if we build a loyalty program, loyalty has nothing to do with reservations, so the aggregate root there might be something different, like a customer, for example. In addition, you can encounter situations where a context may require multiple aggregate roots. It's not common. It's far more common to see a single aggregate root per bounded context, but it's not always the case. So some questions that you have to consider are, is the entity involved in most of the operations in that bounded context? In the reservations context, I think we can clearly say that almost every operation, probably every operation, is going to involve a reservation in some way. So it probably makes sense that that would be a candidate for our aggregate root. Another question to ask is, if you delete the entity, does it require you to delete other entities? Well, if I delete the reservation, then I don't really need the time for the reservation. That's not really that important. Arguably, I don't really need the customer for the reservation anymore either. Now, you might say, yeah, but if you delete the reservation, doesn't mean the person isn't still a customer. And that's true, but it does mean that if you delete all of the reservations for that customer, they're still a customer, but they're not a customer who has reservations. So from a purely reservation context, we can say that that particular customer doesn't matter anymore because they don't have any reservations. So in fact, deleting the reservation could actually delete the customer. Will a transaction span multiple entities? If the answer to that question is yes, then we can safely say that we have got the wrong aggregate root. Because again, a transaction should not span multiple aggregate roots. So those are the types of questions that we can use when trying to determine the aggregate roots. That should help us build kind of a candidate list. And then from there, it's going to be a matter of looking at that candidate list and saying, okay, it's that one. And that's a little bit instinctual. There's a bit of an art to that rather than necessarily being something that we can do scientifically in all cases.